All right, good morning again. One of these days,
Good morning, Nick. How's it going?
it's going okay. One of these,
Just a quick reminder. I turned in my PA4 on Monday, and you said you were going to grade it yesterday, but you never got around to
yeah,
it. So I was just
I have not gotten to
okay.
it, but I will.
Thank you.
Yeah,
So
thanks for the reminder.
I finished PA5. That was an interesting one.
I saw that too. I don't think I've ever had anybody like finish it like ahead of schedule.
Yeah, I did it all in one run, and
Yeah,
it was pretty. I was very surprised.
cool. All right. Any questions? Any last questions on PA5? All right, I will take that as a no. Um, so let's talk about tree balancing. I've been promising to go over this um, for a while. Started on this morning, got it to read and echo a proper inventory. Now just working on the max val function. So max val is definitely the big trick to the whole assignment, and it can take a few iterations of this to get the thing nailed down. But again, work up to it. Do max val just for an integer return, and then add your dynamic programming, and then do max val that tracks the inventory to get the maximum value. Much more successful than trying to get the whole thing to work at once, because you got to come up with the data structures and decide how you're going to pass information to and from the function, and so on and so forth. So work up to it. So binary search trees, right? We like to have this order log n performance characteristic. Wow, that's there we go. We like to have this order log n performance, right? Which comes from the idea that in a nice full fluffy tree, right here we've got 15 nodes with a total of 4 levels, a total height of 3. And so the height of a tree is proportional to the log of the number of things that you have stored in the tree. If the tree is, sufficiently filled at the higher levels before you move down to the lower levels. And since most of our algorithms, searching, adding, deleting, right, basically start at the root and move down, choosing at each point to go either left or right, whether we're doing that explicitly or through the recursion, that's the effect. We start at the root, we move down, and typically when we get to a leaf node, we're done. Well, if the height is on the order of log n, then, for n pieces of data, it's going to take you at most log n operations to do a search or a delete or so on. And so we get this nice performance out of binary trees. And it's not order 1 like a hash should be, but trees are pretty straightforward to implement. They're very memory efficient and so on and so forth. So this is good. This is our goal, but we want to make sure that the height of our tree is on order log n, right? And 15 nodes, we could store them in a really unbalanced tree like this with a height on the order of n instead of log n. And if your tree has, a height of order n, then your algorithms, search, insert, and so on, are also log or order n instead of log n. And so this is why we care about balance. Balance basically tells us how close are we to this ideal. How close are we to a tree where the height is on the order of the logarithm of the number of things in the tree? And depending on the order in which data arrives, you may or may not end up with a balanced tree. For example, if you receive a set of data in this order, right, which you've seen before, what would your add algorithm do? It would make 40 the root, it would get a 20, put that to the left, it would get a 10, go left, left, it'll get a 30, go left, right, 60 will go to the right of the root, 50 will go right and then left, and 70 goes right, right, and bingo, you've got a balanced tree, right? But, you know, if your data happen to arrive in this order, which, you know, if you're working with data that is sorted or almost sorted to begin with, you get the very pathological tree that really just looks like a linked list. And so if we don't do anything extra, if we just take data coming in and we build a tree using our add routine, for example, we have no control over whether the tree ends up, you know, nice and balanced like this, or really unbalanced like that, or, you know, more typically something in between. So did anybody notice what the height of the database.txt file was in PA4 when you build your tree and you say star dump? Anybody notice what the height of that tree was?
I think it was 20. I want to say 20.
Yeah, it was 20 or 21, but it was something around that. And our database file had 1,000 plates in it, and so, you know, log of 1,000 is approximately 10. So really, we could have fit all that data, those 1,000 plates, into a tree with a height, you know, half the height of this tree that we ended up with. Why was our tree so tall? Because the data came in kind of a random order. It was randomly generated data. And so, you know, we got some of this, but also some of this. Not quite as bad as that, not as good as that. You know, worst case, our tree would have had a height of 1,000. Well, that would be really unusual. That would only happen if our data had arrived sorted. But, you know, a height of 20, that's twice as much work as we have to do if the tree only had a height of 10. So the question is, when data is coming into a tree, how do we stop it from looking like this and make it look like that? And so this is what an AVL tree does. And the idea behind an AVL tree is, you know, rebalance as you build it. So as you bring data in, add it to the tree using our usual recursive algorithms, but make adjustments along the way to try to keep things balanced. All right, I'm screenshotting attendance. So the first thing we have to do is we have to know if we've just added something to a tree. Yeah, a billion nodes can fit in 30, which is totally crazy. And a trillion can fit in 40, right? Which 40 operations, not a lot of work, right? So this is a really big win. So suppose we have a tree that looks like this, and I'm not going to worry too much about the values of the nodes for a few minutes. I'm just going to think of how much stuff is where in the tree, because we want to look at this question of balance. Suppose we've just, you know, inserted this node right here, and this is what our tree looks like. Is this balanced or not? Well, I don't know. We can do the recursive definition, and we'll find that, you know, this is a balanced tree. And if we were to add another node over here, that would still be a balanced tree. But suppose we add a node back here. So if you go through your definition of balance that we used for PA4, right, the left subtree, which is just a root, has a height of 0. The right subtree has a height of 2, 2 hops to the deepest node. 0 and 2 differs by more than 1. So this tree is unbalanced. And it became unbalanced when we put this node into the tree. Before this node was here, that was all nicely balanced. And so doing this insert or this add caused the tree to be unbalanced. So the first thing is we want to be able to detect that, and then we want to make a correction. So you know, we've used this recursive definition of balance. Left is balanced, right is balanced, heights are within 1. But I'm going to describe a different way to measure the balance of a tree, and this is using something called a balance factor. And balance factor of a node, I'm just going to define as the height of the left child of the node minus the height of the right child. And there's no absolute value in here. We actually want this to be signed. So it's the height of the left subtree minus the height of the right subtree. And so you get a lot of practice calculating heights of trees, trying to write in balance factors. So let's look at this leaf node right here. What is the left subtree of this node? What does that left subtree look like? Or how would you describe it?
What do you mean, I guess?
What's the left subtree of this node right here?
Nothing?
Nothing, it's null. What's the right subtree?
Null?
Null, okay. What's the height of a null tree?
-1.
-1. So the balance factor here is -1 minus -1, which is just 0. Alright, what about this node right here? What's the left subtree look like?
It's that subtree.
It's just this thing with a single node. What's the height of a tree with a single node?
0.
0. And the right subtree is null with a height of -1. So here the balance factor is 0 minus -1, which is +1. Here's another node. It's a leaf node, so the balance factor will be 0 again. But now let's look at this one. So what's the balance factor on this node right here?
0 minus 0 plus 1?
Something like that.
Wait. -1?
The height of this tree is 0. The height of this tree is 1. 0 minus 1, balance factor is -1. You got it. Is everybody seeing this? So here's another leaf node, balance factor is 0. And so what about this node? This is our last node. This happens to be the root of the tree. Balance factor there.
That would be 0 also then, right?
So what's the left subtree look like?
Oh, sorry, 1. Because -1, so it would be 0 minus -1.
Well, what's the left subtree look like? So just
It's a single node.
it's a single node. Good. What's the right subtree look like? It's all of this stuff, right?
The height of
It's hard to describe in words. So what's the height of a single node is 0. What's the height of this tree? So if we start at the root, how many hops do we make to get to the deepest node?
2.
2. 1, 2. That's the deepest node, so the height is 2. So the balance factor is the height of the left subtree minus the height of the right subtree. That's a -2. Alright, we're going to be doing this for the next hour and 45 minutes, and we're just going to be like working with all these trees and all these numbers, and it's going to get more and more complex and potentially confusing. So espresso is good. Alright, so the balance factor here is -2. Okay, here's the thing with balance factors. If a tree is balanced, every balance factor will be 0, 1, or -1. Right? So if every node has a balance factor of 0, 1, or -1, your tree is going to be balanced. If your tree has a node with a balance factor of, 2 or more, or -2 or less, your tree is unbalanced. And so another way to see that we've got an unbalanced tree is to calculate the balance factors from this node that we inserted on up and see, hey, there's a factor of -2. All right, so what do we do about this? we need to make some kind of adjustment to the tree. All right, so there's a table that I have, a chart, that shows 4 situations in which a tree can be unbalanced. And this is assuming a tree is balanced to begin with, and now you've added 1 node. And these 4 cases are differentiated by the balance factors of the nodes, looking at the first node that has a factor of 2 or minus 2. And so right here we have a node with a balance factor of minus 2, and on its right we have a node with a balance factor of minus 1. If this factor is minus 1 or 0, right, this is the picture. And so here's a balance factor of minus 2, here's a balance factor of minus 1. This is called the right-right case. So we'll say that this is right-right unbalanced. And we're going to make an adjustment to the tree. And the adjustment in this case is we're going to basically take this child, the node that's balanced by minus 1, move that up to take the place of this node, move this node down to be the left child of this node. So these are called rotations. And the feeling of it is something like this. If this is what our tree looks like to begin with, we're going to sort of do this kind of thing, right? And remember, when we do these adjustments, we need to preserve the order of the nodes. This still has to be a binary search tree. If we don't care about the order, it's easy to rebalance, just move some things around, right? But we still want to make sure that things are ordered correctly. So we're going to take this node here, and we're going to move that up. We're going to take this node and move it down. Well, when we move node 3 down to be the left child of 4, something's going to happen to B. And B is going to end up being the right child of 3. Thank you. Because 3 is going to lose its right child, which used to be 4. So we're going to basically do this rotation around 4, bring 3 down. Let 3 pick up B on its right. We're going to leave the child on the right of 4 exactly as it is, and leave that child's children, C and D, exactly as they are. So here's the general plan. We're going to calculate the balance factors. We're going to identify one of 4 possible cases. So right is when, we've got a minus 2 and a minus 1 or 0. Right-left is when we have a minus 2, but its child on the right is a positive 1. And then left-right, left-left are just the symmetric versions of those. If we have a right-left imbalance, it basically means there's too much stuff to the right of this node, but on the right we have something that's slanted over to the left. And the way we're going to balance that is first we're going to make an adjustment to change it into a right-right case, where we have too much stuff on the right of this, and on that right side we also have too much stuff on the right of that root. And that will be the one that we can perform this rotation and end up with a balanced tree. All right, so here's our right-right case. And the way we do this rotation, we're going to take this node and basically make that the root. We're going to bring this stuff down, and then we're going to take this and adopt it on the right of our original node. So let's put some numbers in here so we can see if this is making sense. Let's suppose we have a 40 and a 20 and a 60 and a 50 and an 80, and we just inserted a 70. And I'll list balance factors here. So there's a minus 2 and a minus 1. All right, so this is a valid search tree. Everything to the left of a node is smaller, everything to the right is bigger, but it's unbalanced, right? The height of the left subtree here is 0, the height of the right subtree is 2. So this is a right-right case. And our adjustment for a right-right will be to basically take this node, bring it up here, take this subtree, bring it down here, and then take the 50, put it on the right of the 40. So the right-right rotation will end up doing the following. 60 goes up to the root, the 80 and the 70 stay the same. This original root comes down to be the left child, And now 40 has nothing on the right. It will adopt 60's left child. And our tree will look like this. It's still a binary search tree, 20, 40, 50, 60, 70, 80. And it's really nicely balanced. In fact, if we add one more piece of data here, it's going to be a perfectly balanced, completely full tree. But now if we calculate balance factors, these are 0, these are 0, this is 0, this is 1, and this is 0. So it's like almost a perfectly balanced tree. If all your balance factors are 0, then you've got a nice, completely filled in tree where everything has exactly 2 children or no children. Alright, so we're going to go through some examples of this. But the important thing here is that, you know, this preserves the search order. And if you look at the search order of say, this right case, what's the order of the data? Well, it's everything in subtree A followed by 3, everything in B followed by 4, everything in C followed by 5, followed by D. That's an in-order traversal, so left node, right, so B4, and then down here, C5D. If you look at the sort order of this tree, right, we traverse the left first, which we do in order, so it's A, 3, B. And then we do the root node, and then we traverse the right in order, so it's left, node, right. It's exactly the same search order. So we're not breaking the ability to use this as a binary search tree. And if you go back and you look at this original case, if we're doing, say, a right-left rotation, traverse this tree in order. Well, first we're going to do the left node, and then the root, and then we're going to traverse the right tree in order, which means traverse the left subtree in order, which will be B4C, and then print the root node 5, and then print the right child, which is D. And again, it's exactly the same order. So making these changes don't disturb the sort order of the tree, and that's critical. All right, so let's build a tree. So somebody give me a small integer. 4. All right, there's the root of our tree. And there's only one node in there, so we know it's going to be balanced. But if we calculated balance factors, this has balance factor of 0. All right, somebody give me another small integer. 2. So 2 is going to go to the left. And now if I look at balance factors, this has a balance factor of 0. This has a balance factor of 1. The tree is still balanced. All right, another integer, please.
Someone said 3.
3, okay. So at 3, we're going to go to the left of 4, we're going to go to the right of 2, that's going to come down right here. And now this has a balance factor of 0. What's the balance factor of this node here, the 2 node?
-1? No.
Excellent. The left subtree has height -1, right subtree has height 0. -1 minus 0 is -1. And then what about the root node? What's the balance factor there?
-2?
Almost. So what's the left subtree looks like this. What's the height of this tree?
Is it 2?
Yeah, it's positive 2. So the height of this will be 1, the height of the right will be -1, so it's 1 minus -1.
Wait. Height is, I thought you said it's 2, not 1.
The height of this tree is 1. The height of the right subtree, null, is -1. 1 minus -1 is 1 plus 1. which is 2. So you get a lot of practice with like adding and subtracting negatives. But visually, the balance factor is basically saying, you know, kind of how much stuff is on this side versus that side. And the way we define this was height of the left minus height of the right. That's sort of arbitrary. I could have defined it to be height of the right minus height of the left. Nobody would know what the heck I was talking about if I tried to go to a conference on trees and I used that definition. But I could use that definition, and all of my numbers here would simply change sign. The left-right case would be -2 followed by +1, and so on. So there's nothing magic about left minus right, except that's the convention, right? It's like writing arithmetic formulas from left to right. That's just a convention. So there's a balance factor which is bigger than 1 or smaller than -1. The tree is unbalanced there. So which of these cases applies to this tree with these balance factors shown in parentheses?
Left, right.
Yeah, that's a left-right case. And we're really just matching these templates. Hey, here's a node with a balance factor of 2. It has a left child with a balance factor of -1. That's all we need to say, hey, this is a left-right case. All right, so, yeah, go ahead.
Then you just put 2 as the first node, right? And
so in this case, we're going to take this node and leave it the same, right, to get to the left case. But we're going to take that lowest node, the 3, and basically swap that with a 2 and bring the 2 down on the left, and then pick up 4's left child to be the right child of 3. And you know, these A, B, C, these are just subtrees, and in this case, you know, our subtrees are null, so they're not very interesting. But going from the left-right case to the left-left case, the effect is leave this thing unchanged, right, the node with a factor of 2, but take these 2 and basically swap them with each other. So we're going to take the 4 and we're going to bring down a 3, and we're going to bring down a 2, right? So move the 4 up and bring the 3 down. So again, you can think of this as a rotation. If this is what our tree looks like, we're going to change it into that. So 4 will come up here, and 3 will come down to the left. So move the 3 up here, bring the 2 down on the left, and then if there was something to the left of this, that would go over here. All right, so we've done a left-left rotation, or, you know, a left-right, to get to a left-left case. And if we look at balance factors here, this is 0, this is 1, this is 2. And so now we're in the left-left case, and the procedure here is take this node with a balance factor 1, make that the root, and bring the old root and just put it down on the right of that node that you moved up. And so the 3, here's our left-left rotation, the 3 will become the root, the 2 comes down there, the 4 goes over there, and beautiful, we got a nicely balanced tree now. So this is one approach to tree balancing. All right, questions about this? Can you provide, let's see, it seems really complicated code since there's so many node changing, it could accidentally cause a seg fault. So, just about anything you do with structures involving pointers could cause a seg fault. But if you are doing these operations, you're not going to seg fault, right? Guaranteed. If you're doing exactly these things. But if, for example, you know, this node was null for some reason, and you tried to use that thing's right child and set, you know, this thing's right child equal to that, yeah, that could throw a seg fault. You definitely need to be conscious of what your variables are, and, you know, could they be null, and so on and so forth. And so implementation is a different issue, and I'll show you an implementation in a little bit. But algorithm-wise, right, we kind of just sort of follow this recipe, this prescription, to say, okay, first calculate the balance factors, figure out which case you're in. If you're not in one of these cases, you don't have an unbalanced tree, right? Because, you know, an unbalanced needs to have either a 2 or a -2, and it's going to have either a 1 or a -1 child. And then, you know, the right-left case, 2 steps, and you can go directly from right-left to balance, but usually we think of it as going from a right-left to a right-right. So first, adjust this lower part, right, by taking the 4, bringing it up, putting the 5 down to the right, and then if 4 had something on the right, pick that up on 5's left. So now you got just a right-right case, and now we just do this rotate, where we basically take the 3 and bring it down here and move the 4 up, and then if we had a B child of 4, we can pick that up on 3's right, so it's not abandoned. Now this does not work if your tree is very unbalanced. If you insert 10 numbers into your tree and then start trying to calculate balance factors, this will not work, right? This is working assuming that, you know, as soon as you insert something or remove something, you recalculate balance factors and you make the appropriate adjustments. Yeah, question?
Oh crap, my mic was on once.
Oh, no problem.
I guess my question is this: could you make a recursive or loop to continuously check if the tree is balanced, and continuously check if the tree is balanced, and continuously shift these, or rotate rather, these the nodes around?
So you basically, after you do an insert or a delete, you go ahead and you calculate balance factors. You look for an unbalanced point, and then you do one of these or 2 of these adjustments. It's not necessarily recursive, but it usually comes at the end of a recursive procedure. For example, a recursive add, where you're adding something to a leaf, or a recursive delete.
So if we were to make a balance function, or remake PA4 to make it where it's always balanced, would you kind of add a function called like tree balance, where every time you add a node, it checks if it's balanced, and then it readjusts where the node goes depending on the situation?
Yep, exactly.
Okay.
So so here's my PA4 code, and we looked at some of this yesterday. And I've got a function called adjust, which basically checks balance factors and then performs, you know, the appropriate rotations to restore balance to a tree. And so, for example, in the delete function, if I find I'm deleting the root node data, you know, I've got my 3 cases, but at the end, after I've done my deletion, before I return the root, I do an adjustment. And, you know, if I'm deleting something way down in a tree, if I've got, you know, a tree with a whole bunch of stuff in it, and somewhere down here is a root that I'm deleting, right? That's where I need to worry about adjusting. the stuff above this is not going to be affected. But potentially when I remove this, I'm going to move something from here up. This side might get too short, and I might end up with my tree lopsided to the right. And so, so I do an adjustment at the root after I do the deletion. If I've got something on the left but nothing to the right of the left tree's root, then I go ahead and I do my simple adjustment, but then I also do my adjust. Otherwise, I do the loop that we looked at the other day. Find the largest node, adopt the largest node's left child on the parent's right side, set the largest node to point to the root's left and right children, free the root, but then before returning the new root, I call my adjust function. And so adjust is this magic function that does all of this rotation and checking stuff. So same thing with insert, right? If I'm inserting a new node, I create a new node. Or if I'm inserting to the left, I do my insert, and then I adjust the root, and so on. So adjust is a separate function, and so I put this together a few years ago. Mainly the first time I decided to teach AVL trees. So how do you figure out something? Well, code it. It's a good way to learn an algorithm. So here's the balance factor code. That's trivial, right? Just take the height of the left subtree minus the height of the right subtree, return it. If there's no root, the balance factor is 0, because a tree that's empty is there's nothing there. So that's our base case. So BF takes a node and returns a balance factor. That's straightforward. All right, so how do we adjust a node? If the thing I'm trying to adjust is null, I just return it. Otherwise, we've got 4 possibilities, right? So the first possibility is that that the root of our tree has a balance factor of 2, and its left child has a balance factor of -1. So I check for that. If the balance factor of the root is 2 and the balance factor of the left child is -1, then I need to do this so-called left-right adjustment. And so I change root to be the tree that I get when I do left-right on the tree. And I don't exit at that point, right? I go ahead and I check to see if the root has a balance factor of 2. And if it did not have a child with a balance factor of -1, I know I'm in the left-left case, in which case I want to do my left-left adjustment. But if I started off in the left-right case with a 2 and a -1, I made this left-right adjustment, and now I know I'm going to be in this case. And so all I have to do is see if the root has a balance factor of 2, and if it does, I'll do my left-left adjustment. And then here's the other 2. I could have returned after this point, but here's my other 2 cases on the other side. So a right-left case where the root is -2 and the child is 1, and the general right-right case where the root is -2. So now all you got to do is you got to code these 4 functions: left-right, left-left, right-left, and right-right. And if you've got the pieces in place, there's almost no work to do in writing these, because it's really just following these operations to change this tree into that tree. So more comments than code, perhaps, right? This is the whole left-right function. This is my block of comments describing what's going to happen. So left-right looks something like this, and I took these pictures directly from a website, right? So I'm calling my subtrees 53D, A4, B, C, and I want to change it into this. And we know that the root is, this node with a balance factor of 2. All right, so how do we do our left-right adjustment? So I've got a bunch of temporary variables. I've got an N5, which represents node 5. N4 represents node 4. N3 represents node 3. A, B, and C represent these subtrees. And I'm initializing them to null just to simplify my coding, so I don't have to do a lot of ifs and checks along the way. All right, so I'm trying to turn this into that. So if node 3 is null, I don't have to do anything, right? If 5 has a null child on the left, I don't have to do any work at all. Otherwise, I'm going to set A to be N3's left child. I'm going to set N4 to be N3's right child. N4 could be null, right? If it is, I don't want to say N4 left or right, but if N4 is not null, I'll set B and C to be the children of node 4. And so once I get down here, I know that I've got N3, N4, A, B, and C all set up. And now it's pretty straightforward. What do I want to do? N5 right, I'm not going to change that. I'm not going to change D at all. All I'm going to do is change N5 left, which used to be 3. I'm going to change that to be node 4. So N5 left equals node 4. And node 4's right child is still going to be C, but node 4's left child should now be 3. So assuming node 4 exists, right, if it's not null, I'll set its left child to be node 3. And I don't need to set its right child to be C, but I did anyway. But that's what it would have been to begin with. And then the last step of this is if node 3 is not null, it needs to pick up node 4's original left child, B, on its right. So if N3 is not null, N3 right should be set equal to B. And then I return the root of the new tree, which is still node 5. So that gets returned.
Does this work for, like, you know, does it matter of how large the tree is?
Nope. And this will work for pretty much any size tree. Because we're going to call this, for example, if we're inserting, we're going to recursively go down a tree, move from the root, go left, right, and so on until we get to a leaf node. And then we're going to tack something onto a leaf. And so if this is the node we tack on, maybe its parent's parent is going to have a balance factor of 2 or minus 2, right? The previous part of the tree doesn't really get involved in this, all the stuff above that. It's really just an adjustment we have to make down here. For example, take this and change it to that, and the stuff above it remains unchanged. So when we do our recursive call to add, and the add actually happens in the base case, that's when the adjustment will get done. And it's once you feel like you're pretty comfortable with recursion, this is a fun algorithm to think about, because it'll remind you of when recursion seemed totally bizarre and nonsensical. And it sort of takes that to a new level. So there's a left-right adjustment. Left-left is very much the same. A little simpler to code, right? So initialize everything to null. N5 is the root. D is N5's right child. And N4 is N5's left child. And then basically just take node 5, have it adopt C on the right. So node 5 is going to move down, 4 is going to pick up node 5 on the right. So C is going to be orphaned. So we have node 5 pick up C on its left. That happens right here. And then we have node 4 pick up node 5 on its right. So node 4 right equals node 5, and then return node 4 as the new root. And that's the whole left-left adjustment.
By the way, are you going to post the code and the diagram on Canvas?
I'm probably not going to post the code. I can post that diagram.
Yeah, that's fine.
I just ripped it from the web, though.
Oh, okay.
The ST rotations, and I think it's on Wikipedia. Actually, I think they changed it a while back, but I saved a screenshot. Yeah, I'll go ahead and post that on Canvas. Alright, and then the right side cases, right, left, and right, right, are exactly the same. They're just mirror images of them. And that's the whole adjustment algorithm. And amazingly, it works. And I had no idea when I wrote it up if it was going to work or not, but it actually does. But this is, you know, a pretty classic example of this idea of, how do we do this operation? Well, this is an operation that's hard to understand even on paper, right? But lots of temporary variable names, right? And in this case, I gave everything here a variable name and made a pointer to it, whether I needed it or not, right? I don't actually do anything with node 5's right child in going from here to here. It's just going to stay there. But I still went ahead and put that inside a variable D, just because, well, down here. And this is an algorithm that's a lot easier to understand on paper than it is through code. And that probably varies from person to person. For me, I've never had luck reading pseudocode to really understand an algorithm. The only way I ever really understood algorithms was by working through them on my own on paper. And the pseudocode might, help me work through those steps, but it's really, taking the pictures and moving things around, or taking things and putting them in a queue and bumping up indices or things like that helps me understand algorithms. But usually when you go to like an algorithms book, or you look at a web page that describes, a certain algorithm, what you get is pseudocode. And when I'm at the point of ready to write C code, pseudocode helps, right? Because it lets me capture the steps without worrying about, syntax and specifics about C and so on. But to understand the algorithm itself, I usually have to go to a lower level. I have to go to something visual, or I have to go to lots of examples on paper. I suspect that's different for different people. But, find what works for you. If you love reading pseudocode, that's great, because, that's an easy thing to put in print. It's an easy thing to find online. If you need pictures, that can be trickier, but you can make your own pictures, and then you can make the pictures that make the most sense to you. All right, other questions or comments?
Well, I have a question, but it's not related to this. It's really about dynamic programming.
Okay.
Was working on PA5. I was trying to figure out. I got the code working, but I think what I got stuck on is being able to save data into another array, or maybe I'll work on that last. But I just need to understand, like, how do I access data, or how do I tell the computer to, or give a reference to which data I want to access in the array based off of the recursive algorithm.
What is this data that you're trying to access?
I think he means the caching.
Yeah, I'd like the caching part of it. I was wondering like how that actually works.
So
Thanks somebody to clarify that.
For me, I just created an array of whatever your max val returns, which is an array of structs for me, and then for caching, I just use the capacity as an index.
So if you're working with some kind of structure, like let's say you have a structure called answer, and it's got an integer with a value in it, and it's got item counts. Right, so answer has two fields. Value is the value, right, that you can get out of your bag. Item counts is an array of how many of each item you need in order to get that value. And so your max val would be, a struct answer max val, and pass it a capacity and so on and so forth. So your cache, yeah, exactly what you just said. You can make an array of struct answer, save 1025. Do some kind of initialization in there, and maybe we can, put a valid field in here if we want. and a 1 in here means it's valid. 0 means we haven't stored an answer there yet. So make an array of struct answer. This can be a global. That's our one legal global. Do some initialization in main to set all of your valid flags to 0 maybe. And then in maxval, right, if save bracket capacity dot valid, if that's true, then just return save bracket capacity. Otherwise, do all of your recursion, right? Spend all the time and memory doing the recursion, and then at the end, if you have a final answer that you're ready to return before you return, just save that. Save bracket capacity equals, final, and then return final. Something like that. If you're not doing the inventories, then these struct answers are just integers, right? And you just have a value, and your save array is just an array of integers, and you just save your best value at the index given by capacity. But when you move to storing the item counts to get that value, then you need some kind of structure like this. All right. Other questions? All right. Let's take a 5-minute break. And let's come back and talk about, I think we'll talk about tries. But I'll see if I can find my try worksheets. So I'll come back in about 5 minutes.
since we can have this conversation later.
All right. So let's talk about tries.
Just watched a video of a Russian commander walking through a town with live grenades in his hands, so he can get lynched.
Huh. Yeah, the world's got some issues right now. Because I guess COVID wasn't enough.
You have a frame counter on here.
I have a frame counter?
Your screen recorder, the one that records your paper, it says the FPS on the top of it.
Really?
GovView.
That's weird. I do not see that. Oh, yeah, there it is, right. Yeah, GUVC view.
29.8.
Yeah, something weird happened. I think normally I have it like this. So that's off screen. But my setup was weird today for some reason. Let's see. Worksheets, tries. All right. So, let's talk about tries. And tries are a different version of a search tree. Something we can use to store information and retrieve it pretty quickly, much better than order n. And a binary search tree is built on the idea of, each node has 2 children. It's about the smallest tree that you could have without actually being a linked list. A try goes in the other direction. It makes nodes that are really, really wide. And the nodes of our try typically look something like this. If we're storing, say, words, uppercase words, each node would have 26 children, 1 child corresponding to each letter of the alphabet. So these things are memory hogs, right? Your nodes get really big, but they're extremely time efficient. And so here's the idea. Suppose you want to store the word cat in a try. So we have 26 children. Each of them start off pointing to null. So at the 3rd child, which is C, instead of being null, we're going to make a pointer to another node. And in this node, the first pointer, which we call A, instead of being null, is going to point to another node. And in that node, the 20th pointer, which we call T, is going to point to another node. And in that node, we're going to set a flag. There's a flag at the end of each of these that we call end of string. And that's initialized to 0. But here we're going to set that flag to a 1. And so now I have a try containing a single word, cat. And how do I know there's a cat in there? Because I'll look at the first letter as C, I'll follow that to a node. I'll look at the second letter A, I'll follow the A pointer to a node. I'll look at the third letter T, I'll follow the T pointer to a node. I'm at the end of my string, I'll search the flag in this node. End of string is 1. That tells me I have cat stored.
Very brief question about that. Wouldn't there be a null terminator at the very last row there? Or is that a different topic?
So we're just going to store the letters of a string. We're not going to store the null terminator that comes at the end of the string.
Okay.
But we'll use it to know when we've hit the end. Alright, suppose you want to store cats. Well, let's store car first. So we'll start off with the first letter is a C. It's already pointing to a node, so we'll just follow it to this node. We'll look at our second letter A. The A pointer is already pointing to a node, so we'll follow that. The third letter is an R. The R pointer is currently null, and so we'll create a new node, and we'll have the R point down to that new node. And now we're at the end of our string, so we'll set the end of string flag here to be a 1. Now we've got a car stored. Alright, now let's store cats. So how does this work? We'll start with a C. That's pointing to a node, so follow it there. Second letter is an A. That's pointing to something, so follow to that node. There's a T. That's pointing to something, so follow to that node. Now we want to do an S. So find the pointer that we call S. That's currently going to be null, so we'll have that point to, let me just go over here for more space, have that point to another node. We're at the end of the string, so in this node, set the end of string flag to be 1. And so now we got cat stored. Got the basic idea?
Yeah.
So it's almost, you know, the same kind of procedures that we do with binary search trees, but instead of moving left or right, we move to one of many children based on, you know, the nth letter of the thing that we're looking for or the thing that we're trying to insert. But it's the same idea of starting from a root, so we have one root to the whole trie. And it has, in this case, 26 children and a flag. And so to search for something, let's say search for cab. Start at the root, look at the first letter is C. It's not null, so there might be a cab stored in our trie. So go to the second letter, come down to that node, look at the pointer called A. That's not null, so there might still be a cab. So follow that to another node, look at our third letter B. Check the pointer called B. In this case, that's null. Bingo, we know there's no cab stored in here. If we want to store the word hi, we'll come over here to the H. And instead of being null, we'll point to another node. And in this node, we'll take the I pointer and point that to another node. And in that other node, we'll set the end of string flag to a 1. Now we've got a hi stored.
Why can't it put the high or the letter I, sorry, with the A right under the same where you store A for cat?
So if I had the H pointing down here, then that would mean that H A R was also stored in my trie. Right? If H pointed to this node, that would say, okay, if I have an H followed by an A followed by an R and the string is 1, HAR is part of my trie. Does that make sense?
Kind of. It's hard to get my head wrapped around it.
So let's do an official looking version of this. So let's store a cat. So C comes down here, A comes down here, T comes here. There's our end of string. So there's cat, and I'm just going to write the word over here that this end of string corresponds to. We don't actually do that, but just to keep track of it. All right, so cats, C comes down here, A comes down here, T comes down here, S should go to another node. And we'll set the end of string there. There's cats. If we want to do dog, we're going to have a D. It's got to point to a node that will capture the fact that there's an O, right? So if I point the D down here, then, you know, I've got a D followed by an A followed by a T. I've got that in my try, which I don't necessarily want. So if I want dog, I'm going to bring this down here. There's my D. I'm going to bring my O and point to another node. I'm going to take my G, point to another node. And then on this one, I'm going to have my end of string set. And those are zeros. And everything I haven't drawn is taken to be a null pointer. And so this is dog.
So each node just holds the alphabet or something, or?
Each node has 26 pointers, one for each letter of the alphabet. And so,
Okay, and how do you dictate a word? Just a couple indexes, or?
So you find a word by following the appropriate pointer for each letter of the word. Start with the first letter of the word, say cat, follow that pointer to another node, follow the pointer for the second letter, which is an A, to another node, follow the pointer for the third letter, which is a T, to another node. If we're looking for the word CAT, check the end of string flag in that last node we got to. So if we wanted to store cab, right here we can reuse some of our nodes. We want to start with a C, follow that to a node. We want to follow that by the letter A, so follow the A pointer down here to a third node. But we want the third letter of our word to be a B, so I'm going to take this B and point that to another node. And then I'm going to put the end of string here. That's going to be a cab. So C goes down to A, goes down to B, goes down to end of string. And if I want to do cabs, I'll follow the C, A, B down to here, and I'll take the S over to here and set the end of string. Now I've got cabs. So if the beginning of two words are the same, they will share some nodes, right? Cat and cats and cab all start with a C, so they all come off of this node down here to the second node, and since they all start with a CA, they're all going to branch off of the node that the A points to, which is this node right here. But cab is going to come off here, cat and cats is going to come off here.
I see. So there's like a next node at that B, for example,
Mm-hmm.
that goes to the S.
Yep.
Okay.
Yeah. So this is pretty expensive memory-wise, right? We have potentially one node per letter of each word stored in our try. So if you had 1,000 words with 6 letters each, you might end up with 6,000 nodes, and each node has 26 pointers to it, and each pointer is 8 bytes. That's a lot of memory. But the lookup speed is really, really good. The number of operations we have to do to find a word or to get somewhere that we want to insert a word is on the order of the length of the word. So if we suppose that no word has more than 18 letters, you've guaranteed 18 operations or fewer to look up any word in this dictionary. So it's kind of order 1, right? Order 18 is the same as order 1. Fixed amount of time no matter how much stuff you put in here. So this is very time efficient, fairly space inefficient. And in general, you know, most algorithms, our trade-off comes to space versus time. So an array, right, takes very little space, but potentially a lot of time to do things to. It's order n. A tree takes, you know, more space than an array because we have a pair of pointers in addition to each piece of data. So it takes more space, but it's more efficient time-wise. A trie takes a lot of space, but almost no time to do a search or an addition. And so in general, you know, when we look at ways to do different types of operations, we're going to talk about sorting next, we can choose where we want to be in this space-time graph within reason. Now, what we'd really like to do is be right here. Have an algorithm that takes almost no memory and almost no time. Those are hard to find. What we really don't want is to be up here. An algorithm that takes a lot of memory and also takes a really long time to run. Now we're playing, you know, a Steam game or something. So we can navigate this space-time graph by judicious choice of algorithms, but there are some constraints. We don't generally get to just pick a point on this graph and say, okay, I'm going to use an algorithm that, you know, takes almost no memory and runs instantaneously. We don't get to do that. But there's usually some sort of you know, approximate band of possibilities that we can choose from. And if we're doing something where we really need quick retrieval and people are willing to pay, you know, a ton of money for this, we can buy more space. We can buy more memory. We can buy bigger hard drives or whatever. You can't buy time, right? If somebody wants you to sort a bunch of numbers, you know, really quickly, they can't just throw more money at you and have you buy, you know, something that will sort more quickly. You can buy a faster CPU, better cooling, and so on and so forth, but space is usually more accessible, right? You can make a system with more memory, and so navigating the space is kind of one of the aspects of studying algorithms. All right, so questions on how tries work. That should be enough to do your quiz, by the way. Deleting from a trie is tricky. And the easiest way to delete is just, you know, change the end of string. So if we want to delete cab, I'll just change my end of string from a 1 back to a 0. And now if I search for cab, I'm going to start with a C, come down here, follow the A, come down here, follow the B, check the end of string, it's a 0, cab's not in here. But I can't... Say again?
Isn't cab still in memory though? You could just, but changing end of file just means that you're not referencing it anymore.
Yeah, and it's a really sloppy delete because of that. So this node is still in use. Now I need this node to be in use because I need the S pointer to point down to cabs. So really the best I could do to delete cab is change this to a 0. That's exactly what I would have. But if I wanted to delete dog, right, and I simply change this to a 0, well, I've got this node in use now that I don't really need, right? I could get rid of this. I could change this back to a null. And in fact, I could change this back to a null. And in fact, I could go all the way back up here and change this to a null. And maybe it's worth doing that, or maybe it's worth just changing this to a 0, and then if I come up with, you know, dodo or something like that, I've already got my D, it's pointing to an O, and I can just have that point to something down here and come off the D and keep going like that. So deletion is a different matter, but if your goal was to, you know, harvest data, if you were just scraping words from, you know, a live news feed and building a database of these, Try might be a really ideal structure for that if you have the memory. But you know, big nodes, lots of RAM. But the order of complexity is so good in time that, you know, even if I have to store these things on a hard drive in a file or something, it might still be worth it, depending on how quickly I need my retrieval to happen. So tries are kind of like another end of the spectrum from binary trees. Super wide nodes, but not very deep. So depth of the try is basically the length of your longest word. All right. Other questions, comments?
I kind of want to break this thing a little bit. What would happen if all of the nodes in the first struct got filled?
That's totally fine. That means that you have at least one word beginning with each letter. But, you know, any word that begins with a letter C is going to be pointed to by something coming off of the node that C points to. If it's CA, it'll come off of here. If it's CE, it'll come off of there, and so on. But I could have, you know, a million words that begin with the letter C. All of them I would start off from this pointer right here and come down to here. And then I choose a pointer based on the second letter of my word. And if I have a bunch of words that start with CA, that's okay. I'd come down here and I'd choose a pointer based on the third letter of the word. And eventually, you know, my word will be different from some other word, and those two words will come off different pointers. And so your tree kind of, you know, separates out like that.
I'm kind of curious, is there different kinds of tries, or is it only for strings?
So this example, I'm just doing strings, but you could do this with other things. You could do this with binary data if you wanted. It depends how big you want your tries to be, how big you want your nodes to be. But I'm doing this with letters. I mean, I could do this with 256 pointers, one for each possible value of an 8-bit byte. And now I could store, you know, a string of bytes using this kind of structure. My nodes are ridiculously huge, but, you know, quick retrieval based on the number of bytes that I have. And the structure of it, you know, is like this. Right, so root node, 26 children, each of those children, 26 children. And each of those children, 26 children. And so for a height of n, right, you've got on the order of 26 to the n possible nodes, which goes along with the idea that if you have a word with length n, right, there's 26 to the n possible words. CSE222A product rule, right? How many ways can you form a word with n letters? It's 26 raised to the n. So that's the frightful memory consumption of a try. If you have n levels, 26 to the n nodes. All right. So new topic. Let's talk about sorts. So sorting is a classic problem in computer science. It's one of the things that computers were originally conceived for. So, you know, 1890 census, Hollerith, all that stuff, tabulating entries from the national census. So sorting, right? We want to organize information in some kind of order. If we have integers, we typically, order it from smallest to largest or largest to smallest. If we have words, we alphabetize. So we're ordering by ASCII codes, basically. But the general question of, how do we sort a collection of data? And the answer, to some degree, comes down to, space versus time again. How much memory am I willing to use, and how quickly do I need to sort? And for us as programmers, it also comes down to how lazy am I feeling. If I don't want to do a lot of work, I might code a sort that's not very efficient, but doesn't take too much work to write the code for and get it running. If I'm being paid, big bucks to write a super efficient sort, I might spend, a month coming up with a new algorithm and coding it, and it might be extremely efficient. So I want to talk about a few different types of sorts, and as we're doing this, I want to keep looking at order of efficiency. And remember, this idea of big O notation is talking about, as the size of a problem grows, how does the time it takes to do that problem increase? And so order n is linear. If you have twice as much data, it takes you twice as long. And that's kind of how we imagine, life to be. If I have to paint a room that's twice as large as the one I did yesterday, it's going to take me twice as long to paint. And, that's maybe a good first order approximation, but, if I try to paint a room that's 100 times as large as the one I painted yesterday, it's going to take me more than 100 times as long. Because, it's probably tall, I'm going to have to get, things that I can stand on, and I'm going to have to get an extension for the roller to do the ceiling, and I'm going to need more drop cloths and all this kind of stuff. So sometimes, when a problem increases in size, say doubles, the time it takes to run an algorithm is more than doubled. And so a common example is n squared. Double the problem size, quadruple the amount of time. With things like binary trees, we sometimes see, a logarithm n, which is better than linear time. So if I have 1,000 times more things, it takes me 10 times as long. So now we've got a winning proposition. Something we'll see a lot with sorts is n log n. So it's worse than n, but not as bad as n squared. It's n times, a little bit more. And we can get, some things like n cubed. So some matrix operations might be n cubed. So you double the amount of data, your time goes up by 8x. And that starts to get bad. Sometimes you get things like n to the n. That's horrifying. Because n to the n grows quickly. 10 to the 10 is a whole lot bigger than 1 to the 1. And sometimes things get really nice and we get something like order 1. That says no matter how much data you have, it takes the same amount of work to manipulate it. That's the ideal hash, for example. So I want to keep these in mind and come back to these. And these are good to know for exams, by the way. It's a random comment there. So let's look at probably the first sort that people usually start with, which is a good old bubble sort. And a bubble sort, order of 1 over n, that would be interesting. That would take less time the bigger the problem was. Yeah, I forgot order 0 actually. But yeah, order 1 over n would be cool. More data, it takes less time. I don't know if that happens, but it's a cool concept. I'll have to think about that. All right, so I think everybody here has coded a bubble sort. I think you probably do this in 121. What's the basic setup here? Start off with a set of let's just work with integers. So 5, 2, 8, 7, 1, 6, 3, 9. And with a bubble sort, what you do is you make a pass through data, you usually start at the beginning and you move down through the end. And you compare each number to the number after it. So throughout all of this, I'm going to try to sort from smallest to largest for no reason. But that's going to be our general goal, smallest on the top. So you make a pass through your data, and basically you compare each number to the number after it, and you say, are these two numbers in the correct order? And if they're not, you swap them. So if I want smallest at the top, 5 should be smaller than 2. Well, those are in the wrong order, so I'll swap my 2 and my 5. Now I'll compare 5 to 8. Those are in the correct order. I'll compare 8 to 7. Those are in the wrong order, so I'll put the 7 here and the 8 here. I'll compare 8 to 1. Those are in the wrong order, so I'll put the 1 here and the 8 here. Compare 8 to 6. Those are in the wrong order, so I'll swap those. 8 to 3. Those are in the wrong order. And then 8 to 9. Those are in the right order. And so this is one pass through our data. It doesn't leave our data sorted. But what is the effect of that one pass? What happens after you've gone through the data once like this?
The largest number is where it should be.
The largest number is where it should be, which is right at the bottom. So it's called a bubble sort because, you know, bubbles are lighter than the liquid they're in, and so they rise to the front. But you could also call it a rock sort because the heavier rocks sink down to the bottom. So the biggest number will be in the bottom position after one pass. Well, it happened to be in the correct position to begin with. That's okay. We're guaranteed after one pass the biggest number will be down here. And now we're going to make a second pass. And we're going to do exactly the same thing. Well, 2 and 5 are in the right order. 5 and 7 are in the right order. 7 and 1 are swapped, so we'll switch those. 7 and 6 are swapped, so we'll switch those. 7 and 3 are swapped. And there's an 8, and there's a 9. And so after this pass, we're guaranteed the second largest number is in the second to the end position. And we just keep making passes through our data. So the 2 and the 5 are okay. The 5 and the 1 should be swapped. 5 and 6 are fine. 6 and 3 should be swapped. 6 and 7 are fine. There's our 8. There's our 9. And now the third largest number is in the third largest position. And you might notice that as we're doing this, you know, we're trying to move the third largest number into position, but we've also moved the fourth largest number. That just happens to be how it worked out because we started off with the biggest number in the correct spot anyway. So we make another pass. The 1 and the 2 will swap. The 5 stays there. The 3 and the 5 swap. The 6 stays there. The 7, 8, and 9 are correct. Now the 6 is in the right spot. Do another pass. 1 and 2 are correct. 3 is correct. 5 is correct. Nothing's going to change. But we know that the 5 is in the correct position. And we'll do 3 more passes, or maybe 2 more passes. And when we're done, we know our data is sorted. Alright, so that's a bubble sort. And it's pretty straightforward to code.
Kind of curious what order would this be? Would this be order n, if I had to guess?
So yeah, let's look at the order. So for pass equals 1 to n, what do we want to do? Go through data and swap pairs as needed. There's our pseudocode for a bubble sort of n pieces of data. So make n passes, and each pass go through the data and swap pairs as needed. So what does this look like? This is a for loop. So let's go for j equals 1 to n. If data j is bigger than data j plus 1, swap those. And I'm being really reckless with edges here, right? Technically, we only want to go for j equals 1 to n minus 1 because we're comparing element j with the element after it. And if we have n pieces of data, right, I only want to go up to n minus 1, compare that to n. And I've switched my index from 0 to 1 because this is pseudocode. And I want to think about n passes, so I'm going to call my pass 1 through n. But, you know, my indices should start from 0, so this should be from 0 to n minus 1, probably n minus 2. I don't want to bog down in those details, right? We're looking at algorithms from a high-level perspective, and we're going to do approximate orders of complexity calculations. So I'm going to be kind of fast and loose with the edge cases here. But ballpark, right? We're going through the data means make a loop, look at each piece of data, compare it to the piece after it, and if they're out of order, swap them. So this operation, this for loop, this is pretty clearly order n. It's a for loop that executes n times. And, you know, for each pass, we're going to do this comparison. And yes, sometimes we'll do a swap, sometimes we won't. And so we don't know, you know, exactly if we're going to swap every time, half the time, few of the times. But in terms of first order approximation, the amount of work we do is proportional to n. If we're looping from 1 to 10, we're going to do this statement 10 times. Or if we're looping from 1 to 1,000,000, we're going to do this 1,000,000 times. So it varies as order n. So now if we look at our original algorithm is a for loop that runs n times, and the body of that loop is order n. So each of these n times we have to do order n work. This is going to end up being order n squared. And this is nothing more than, you know, if you just wrote for I equals 1 to 10, and in here you said for j equals 1 to 10, how many times does this thing execute? It's going to be 10 times 10. Right, this loop will run 10 times, and this whole loop itself will run 10 times. So this stuff in the middle is going to happen 10 times 10, or n squared. So bubble sort is order n squared. And that's not too bad for a small amount of data. If you're trying to sort 20 things, that's totally fine. But if you wanted to sort 1 billion things, this is a really bad way to do it, because 1 billion squared is a lot. All right, you can speed this up though. Right, for example, once we got here to this pass, and we made our pass through and we tried to swap things that were out of order, guess what? We didn't have to swap anything. All of these were already in the correct order. So we could actually modify this algorithm so that if our data is out of order, we swap it and we set a flag. And then our outer loop could simply be, well, the flag has not been set. And so we'll keep making passes through our data until our data is sorted. And that won't be any worse than n squared, but it might be better. In particular, if our data started off completely sorted, our first pass through, we wouldn't swap anything. We could say, hey, we're done. Whereas a kind of blind bubble sort, even if our data was sorted, we would still make n passes through it. We wouldn't do any swaps, but we'd still be, you know, doing a for loop n times inside a for loop n times. And it would still be order n squared. So we could speed this up by looking for, you know, are we done ahead of time? Another thing we can do is notice that, you know, the first time through, we had to compare every number to the number after it. But at the end of that first pass, this number is in the correct spot. So the second pass, we didn't need to do as much work. In that inner loop, we only had to compare up through, but not including the last number. because we know that this number and this number are in the correct order because this is in the correct spot. And the next pass, we know these two are in the correct spot, so we can do an even shorter inner loop. Yeah, go ahead.
So in this case, would you, every time you loop, you set n to n minus 1 in this case? So
Basically.
operations.
Yeah, and I wouldn't do it exactly like that, but that would be exactly the effect. We'd be doing this inner loop smaller and smaller amounts. And so where's the unmodified version of a bubble sort would do 10 plus 10 plus 10, 10 times would be 100 passes. The modified version would do 10 comparisons on your first pass, only 9 on your second, 8, 7, 6, and so on. Which is 55, I think. So it ends up taking about half as much work. Yeah, go ahead.
I was just saying, yeah, it's 55.
Yeah, cool. So this is order n squared. The sum of the first n integers, though, is n times n plus 1 over 2, which is n squared plus n over 2, which is n squared over 2 plus n over 2. Well, when we do these orders of complexity with polynomials, we always pay attention to the term with the highest exponent, and we throw away constant multiples. So this still ends up being order n squared. Even though it's only half as much work, if we double n, this will double, this will double. Sorry, this will quadruple, this will quadruple. So it's still order n squared. So bubble sort, you know, we can do a little better by being a little more clever, but it's basically an n squared sort. And so again, you know, if you've got, you know, a few hundred things to sort, it's not a bad go-to. All right. Another n squared sort is selection sort. And selection sort works as follows. So there's some data we want to sort. So I'm going to have an input list and an output list. All right, selection sort. Here's, sorry?
Can you remember what kind of sorting this is called?
This is a selection sort.
Okay, thanks.
Yeah. So selection sort, we can remember which way this works because the sorting happens when we select or choose data from the input. So let me put this up here. We're also going to talk about an insertion sort, and that's going to sort when we insert into the output. So selection sort, we're going to choose from the input. We're going to select in sorted order. So here's how it works. It's very simple. Go through, find your smallest thing in the input, copy that to your output. And then somehow mark it in the input to say I've already selected this. Now go through, find the smallest thing you haven't selected. That's a 2, copy that to the next place in the output. Find your smallest thing, that's a 3, copy that to the next place. Find your smallest thing is a 4, find your smallest number is a 5, find your smallest number is a 6, find your smallest is an 8, find your smallest is a 9. There's nothing left to select, we're done. So that's pretty easy to do, right? It's just repeated passes through your input data, choosing the smallest at each point. Well, how do you find the smallest element in an array? Well, you're doing this in PA5. You're finding the largest element in some, you know, loop of operations. If our loop was simply, you know, let's look at the ith element of our array, just start off with, 5 is my smallest, and go through each element. And if it's smaller than your smallest so far, remember that. Now 4 is my smallest. That's bigger, that's bigger. Hey, 3 is smaller than 4. That's my smallest. 8 is bigger. Hey, 2 is smaller than 3. That's my smallest. Oh, here's a 1. That's smaller than 2. I'm done with my input. What's the smallest number I found? It's a 1. So what's the order of complexity of this sort algorithm? And break it into steps. There's two things going on here.
What was the question? You said what was the order?
What's the order of complexity of this?
Seems like it's order n if I had to guess.
So
Still n squared?
So how do we decide this, right? The process of a selection sort is, you know, we go through our data, we select the smallest thing that we haven't picked yet, and we add it to the output. So let's look at that first part, going through our input and choosing the smallest. So forget about sorting. Let's just write a function that says, here's an array, tell me the smallest thing in that array. So you know, answer equals data bracket 0 for I equals 1 to n. If data bracket I is less than answer, set answer equal to data bracket I. And then just return answer. So start off with the first thing, say that's the smallest I've seen so far, and now go through all the rest of the data. And for each piece of data, if it's smaller than the smallest thing you've seen, remember that as your smallest piece of data. And when you're done, return, you know, whatever the smallest was you saved. That's how we select the smallest thing from an input array. And what's the order of complexity of this algorithm? If I double n, how much more work do I do? So suppose that n is equal to 10. This is going to say for I equals 1 to 10, how many times am I going to do this if statement?
10 times.
Yeah.
Yeah.
If n is equal to 20, I'm going to do it 20 times. So double the amount of data, the amount of operations, that's order n. This algorithm, this selection, gets me one piece of data in my output. And after I've done that, I'm going to go through and select the smallest thing that's left in here, and that's going to give me my second piece of data. And I do it a third time, it's going to give me my third piece of data. If I do it n times, it's going to give me my nth piece of data. So I have to do this whole loop n times. And inside this loop, I'm doing something n times. So that's going to be order n squared. So basically the same as a bubble sort.
Wait, I'm confused. Did you said order n for the for loop function, but then why is it why would it be n squared?
It's order n to go through my input and find the smallest number. That gives me this. I have to do that a second time to find the second smallest number. I have to do it a third time to find the third smallest number. I have to do it n times to find all of my output numbers. So each selection takes n operations, and I have to do n selections. So if it takes 10 iterations to find the smallest number in a list, and I have to do that 10 times, I'm going to do this inner part. 10 times 10 is 100 times. That's where the n squared is.
Okay.
All right, and then the other version of this, which is very similar, is an insertion sort. And so let me start with my same input. insertion sort, we don't select the smallest thing here. We just start from the beginning. We take the first number and we put it in our output. There's a 5. We take the second number, that's a 4. We put it into our output in the proper spot. So we start at the beginning and we say, here's a 5. Oh, 4 should go before that. There's our 4. I'm going to give myself more space. And then we pick our third number as a 6, and we go through our output and we say, oh, that should go right here. And here's a 9, we go through that, oh, that should go right here. Here's a 3, oh, that should go before the 4. Here's an 8, oh, that should go before the 9. Here's a 2, should go in the beginning, and here's a 1, that should go in the beginning. And when you're done, your list is sorted.
So the way it works is that it's 5 considered like a root, and it would just check if it's greater than or less than until it reaches the end of the list or beginning of the list.
We're really doing what we did when we added nodes to our linked list, right? If we find a new number like 7, we're going to start at the beginning of our output. We're going to find where to insert that 7. Oh, it's going to go right here before the 8. So our output might be a linked list, and we're just inserting in order. And this is really, you know, like a PA1 sort, right? If you kept adding data to your linked list, the data in that list ended up being sorted. All right, I'll be back in a minute. Think about the order of complexity. Talk amongst yourselves. I'll be back in about 1 minute.
No one's talking.
I'm pretty sure it should be n squared. I don't want to look on line and sheet.
What did he say this one was called again?
Insertion.
Okay.
Don't do it. Don't do it.
I
Don't
didn't
open
do
up
it.
Google.
I
Don't
didn't
open
do
up
it.
Google.
I didn't do it.
Don't do
Alright.
it.
I haven't done it.
Come on, Judy, you're stronger than this.
I'm not. You know how you become a good programmer?
You Google it.
You Google it. You know what my boss says when I have a question?
Google it.
He says, have you looked at DuckDuckGo yet? Callum already cheated. Callum, what are you doing?
Seriously?
Come on, Callum. Such a pleb. I already had mine open, so I didn't even need to actually Google it.
But seriously though,
I'm pretty sure all the regular sorts, or any sort of sort that just looks at the data and does basic moving around, is all kind of n squared.
I agree with that actually. They're all like very similar. He says very similar to the selection sort. So it's just a different way of moving it.
Yeah, if you do some optimizations, you can get them down to order n, but most of them are n squared, I think, for these sort of just really basic.
I could have sworn that the first one, the selection sort was order n, but until I realized, oh, you have to run it like n times, but then you have to run it n times again or something.
Mystery, the onion is things that aren't true. This is true.
no, the onion is true.
No. Don't listen to what Dakota just said.
The onion is true.
Onion is not true.
There are many layers.
None of which are true. Boy, are they funny though.
What we really need is to know if we have enough time to discuss gravity sort, because I do not understand that and I want to.
Alright, once you actually get to anything in real world, you'll just use a library. What is a gravity sort though?
It's supposed to be like matrix radix sort, like
Explain something I don't know with something I don't know.
like a sort in place. So there's no actual comparisons. You just sort of like drop the numbers. It's really weird, but
Interesting.
like you have a tens place, you have a hundreds place, you have a ones place. You just sort of drop the numbers and they all fall where they go.
Yeah, we'll definitely do a radix sort too. Those are freaky. Yeah.
We said n squared.
N squared. Cool. Why is n squared?
Because they all seem to be n squared.
Well,
And
that's...
you'd have to constantly go through the array to find the next number anyway.
Yeah, so choosing from the input is order 1. We just take the next thing from the input. But putting in the right place in the output, that's order n. The insertion part, right, this is insertion sort. The process of inserting is an order n operation because, you know, maybe we're inserting something right in the beginning, maybe we're inserting at the end. But we have to kind of go through each number in our output array in order to find the right spot. So the insertion is order n, and we have to do that insert a total of n times to insert each of these input numbers into the output. So yeah, this ends up being n squared. So insertion, selection, bubble, all kind of the same. But they can make a difference in terms of memory. For example, in an insertion sort, if I store my output in an array and I have to put something in the beginning, what do I have to do? I have to move everything in my array down one spot to make space in the beginning. And in general, accessing lots of different memory locations is not a good thing to do time-wise. It defeats an aspect of memory management called caching. And if you access data near other data you've accessed, the cache works in your favor. But if I were to go through my entire array every time and this had, you know, 1 billion elements in it, I'm defeating the benefits of having a cache memory. But if this is a linked list, right, I don't actually move a whole lot of stuff around. We know that to insert in a linked list, you basically adjust 2 pointers. You make a new node, point to the thing that comes after you, change the thing before to point to your new node, and you leave the rest of memory alone, so that'll work pretty well. So an insertion sort, going through the input, very straightforward. Just read off each number in succession for each pass. But choosing where to put it in the output list, well, we have to examine memory, and then we have to pop it into the right spot. Selection sort, we have to go through memory and you know, find the smallest, for example, each time through, and we have to somehow mark it. Either delete it from the array or set a flag saying we've already used this one. But then the process of putting it into the output array is trivial. Just add it to the next consecutive location. So if this is an array, it's order 1, right? If we've got 3 things in the array, we just store the next thing at index 3. And we store the next thing at index 4, and so on. If the output was a linked list, this would be pretty inefficient because you have to move to the end of the linked list to insert. But we could insert in the beginning very efficiently. That's order 1, and so we could, you know, make a list in increasing order by first selecting the largest and then the next largest and so on. Select in the reverse order and insert them into the beginning. So there's lots of implementation details to this. But generally, you know, selection sort, insertion sort, bubble sort, they're used either for like a really quick and dirty implementation, or they're used for, you know, discussing algorithms and thinking about sorts and so on. They're not practical for large amounts of data though, because they're all n squared. And so let's look at a better sort. So this is called a merge sort. And merge sort is a really fun way to sort data. So let me, for no particular reason, I'll stick with my running list of numbers. So here's my 8 numbers that I want to sort, but imagine it's like 8 billion, right? All right. Here's how I'm going to merge sort. I'm going to split my list of numbers in half. And somehow I'm going to sort this list into 4, 5, 6, 9. And somehow I'm going to sort this list on the right. 1, 2, 3, 8. And now I'm going to interleave these into a sorted output. So all I ever have to do is look at the first number in each list. And I say, what's smaller, 4 or 1? So I'm going to look at my 4, I'm going to look at my 1. Which of those is smaller? It's a 1. That's going to be my output. All right. Now look at the first number in each list. I've got a 4 and I've got a 2. Which one is smaller? A 2. So I'm going to put that in my output. Now look at the 4 and the first thing in this list, 3. The 3 is smaller. That goes in my output. Now look at a 4, first thing in this list, and an 8, first thing in this list. The 4 is smaller, so that goes into my output. And now look at the first thing in each list, 5 and 8. 5 is smaller. Now look at the 6 and the 8. 6 is smaller. Now look at the 9 and the 8. 8 is smaller. And now there's nothing left in this list, so I'm going to take the 9 and put that in my output. So the pseudocode looks something like this. So merge sort data. So split data into 2 halves. Sort each of those halves independently. And then look at first element of A and B, copy the smallest to the output, and remove that one from A or B. And just do that until you've cleared out A and B. And that will leave you with sorted data. So take your data, split it into 2 smaller arrays, A and B, sort those, and then go through and repeatedly pick the first element from A and B, and see which one is smaller. Whichever one is smaller, copy to the output and remove from that array, and just keep doing that. And you're going to do that n times, and when you're done, your output will be sorted.
I think I see an opportunity for recursion here.
Yeah, because how are we going to sort our subarrays A and B? We're going to use a merge sort. And what's our base case? If length of data equals 1, we'll just return. Because if we're sorting an array of one number, we don't have to do any work. It's already sorted. So merge sort is a recursive sort algorithm. It takes in an array of data, splits it in half, calls merge sort on each of those halves, and then does this interleaving operation to take those 2 sorted subarrays, put them together into a final sorted output. So if we call merge sort on this array 5, 4, 6, 9, how does that work? Well, we create 2 arrays. A is 5, 4, B is 6, 9. We merge sort both of those, so A becomes 4, 5, B becomes 6, 9. And now we form an output by looking at the first element of each, 4 and 5. The smallest is 4. Take that out of A. Look at 5 and 6. The smallest is 5. Take that out. And look at 6. Well, there's nothing left in A. As soon as we know that one of the lists is empty, we can just copy the other list to the output. And there's the merge sort of 5, 4, 6, 9. If we want to merge sort 3, 8, 2, 1, split it into two lists. A equals 3, 8. B equals 2, 1. Do a merge sort on each half, so B will be 1, 2, and now interleave those. So compare the 1 to the 3, our output is a 1. Compare the 2 to the 3, our output is a 2. And then B is empty, so now we just copy the remaining elements of A. And so there's the merge sort version of that input. And so we take those two merge sorted lists and we interleave them. There's the merge sorted list, we interleave them, and there's our output order. So what's a good guess for order of complexity for a merge sort?
Well, to sort the two arrays would be, I'm assuming, I don't know, n squared, right? At first. It'd be, you'd have to sort two different arrays.
Which we're doing with merge sort, so we need to know the order of complexity of merge sort to find the order of complexity of merge sort. That's recursion.
Oh, I see. Okay.
But we know a base case. We know if our length has data 1, we're just going to return. And so merge sorting something of length 1 takes, order 1. So this is trickier.
And then it seems kind of close to, maybe?
Yeah, this is trickier. The interleave operation is going to be more or less order n. Right? Once I've sorted my left and right halves, I have n pieces of data. This business of choose the smallest of these two, choose the smallest of these two, and these two, and these two, and these two, right? That's going to happen n times. If we have n pieces of data, ultimately to interleave them, we have to do n operations. So the interleave is, more or less order n, except that, when we're interleaving two lists of order 2, this is only order 4 instead of order 8. When we're interleaving two lists of length 4, this is order 8. 8 operations. If these have length 2, it's only 4 operations. If we had two lists of length 1, it would only take 2 operations. So the amount of work we do in here, kind of order n, but it actually gets smaller the more times we split our list. But the more times we split our list, the more recursive calls to merge sort we're going to make. So originally we're calling merge sort with a list of length 8. That's going to require 2 recursive calls, each on a list of length 4. And each of those is going to require a recursive call, each on a length 2 list. And merge sorting something of length 2 is going to require 2 calls to merge sort on sublists of length 1. And then these lists of length 1, those will hit our base case, will return without recursing. So on one hand, we look like we're, going down log n. On the other hand, we have n, recursive calls to merge sort, but these calls get shorter and shorter. And so the amount of work we do in the interleave step gets cut in half each time through. And so as you work this through, what you end up with is a pretty nice order of n log n. So not as bad as n squared, not quite as good as n though. And this is a pretty common complexity figure for a lot of these better sorts. Merge sort, quick sort, heap sort. These are going to be n log n.
I'm trying to think about like a pattern or some way to kind of think about how would you calculate order and complexity, because I'm still not seeing a strong pattern here.
Don't look for a pattern. Think about the analysis. Patterns don't really work, and this one is a really hard complexity to visualize. Bubble sort, insert, selection. are better ones to wrestle with, because those you can do specific cases and sort of see the doubling or quadrupling of the time. But merge sort, you know, we've got two things going in opposite directions. We've got more and more recursive calls each time we divide the list, but the amount of work being done in those recursive calls is smaller and smaller, because we're splitting the lists in half and merge sorting something half as big. So this is a much trickier order of complexity to come up with. But think about, for example, finding the height of a binary search tree, the complexity of that. Or better yet, think about searching a binary search tree. If this tree has n elements in it, how much work do you do to find one element? And it's a function of how many times you have to move down from the root and, you know, jump left or right. That's a function of the height of the tree, which is on the order of log n. So those are probably better examples to think about while grappling with these orders. Binary search tree operations, or for sorting, bubble sort, insertion, selection. Merge sort is weird, quick sort is weird, heap sort will be really, really ridiculous to try to understand, but I'll tell you what the answer is anyway. And then radix sort will be counterintuitive. Alright, so Monday we will continue sorting. We will look at quick sort and radix sort and heap sort. And that will probably be most of what we do Monday, and then Wednesday will be a wrap-up for the course. So the end is near, as they say. Alright, have a good one. I will catch everybody next time. Thank you.
Thank you, bye.
Catch you all in the next video. See you later.
Alright.